Hello and welcome. These are the solutions to practice quiz 8. Which experiment determined the mass and charge of the electron? Thomson's cathode ray tube experiment discovered the electron. Gold foil experiment discovered the nucleus. Dalton's atomic theory just merely proposed the atomic nature of matter. The radioactivity experiments explained the different radioactive pathways for radioactive decay. And the Millikan's oil drop experiment furnished the mass and the charge of the electron. How many neutrons does a cesium-133 atom contain? Well, this is the mass number for that nucleus. So the mass number is the sum of the protons and the electrons. We get the protons from the periodic table. For cesium, that's 55. Remember, just have a periodic table open so that you can check that cesium is element number 55. So 55 protons, we got to subtract that from 133 to get the neutron count. And so that looks like it would be 78. What is the chemical symbol for an element or for an atom with 20 neutrons, 20 protons, 18 electrons? Okay, so we're looking for 20 protons for the atomic number. So that's calcium on the periodic table. 20 plus 20 is the mass number, so that would be 40. And then 2 less electrons, so I don't have as much negative charge, so the positive charge is going to sort of be more predominant. So we're going to have 2 net positive particles, so we're going to have a 2 plus charge. So calcium 40 with a 2 plus charge. So that would be B. Okay, so let's take a look at number 4. Which of the following measurements of length is the shortest? So for this particular problem, what we might do is convert these all to meters. So for A, this would be 1.25 times 10 to the minus 9 meters. For B, that would be 12.5 times 10 to the minus 6 meters. So micrometer is a minus 6 meter. Picometer is minus 12, so that would be 125 times 10 to the minus 12 meters. 12.5 angstrom would be 12.5 times 10 to the minus 10 meters. And then the kilometer, 1 kilometer is 1,000, so that would be 1.25 times 10 to the minus 7 meters. Okay, so we can rule out some of the short ones here. Let's roll out these ones here. Now, 12.5, this would be 1.25 times 10 to the minus 9 meters. So that's the same as this one. So neither one of those are right. And then 125 times 10 minus 12 would be 1.25 times 10 to the minus 10. So the nature of this problem is a little tricky to work it out. I mean, you could just work it all out in the calculator, perhaps. I just did these conversions with the units in my head, so I didn't really employ a calculator to do this. You could have just thrown it into a calculator as well if you prefer. So what is the major conclusion of the gold foil experiment? Well, that's a nuclear model that we talked about earlier. So the plum pudding model is disproved in favor of modern nuclear theory. So the nucleus of the atom was what we're supporting. The plum pudding model is the idea that all the protons, neutrons, and electrons would be interdispersed. That's not true. The study determined the charge of the electron. That's the Millikan's experiment, the oil drop, mass to charge ratio. That's Thomson's cathode ray tube in multiple portions was validated. That's just a proposal of Dalton's theory. It's what leads to the multiple portions. So there we go there. Moving on, number 6, a brick consists of a pure metal. We're given the measurements of it in inches. We're asked to kind of calculate the density. Now, one way you might look at this is just convert those to centimeters and then calculate the volume of the object in centimeters cubed. Of course, you could just go 4 times 5 times 3 for 60. So if you have 60.0 cubic inches, then 1 inch is just 2.54 centimeters, and we just cube that whole factor. And then that's our density, or that's our volume, I mean. Our density is mass per unit volume, so we could take the volume and then divide that into the mass. So 7,020 grams to calculate in grams per cubic centimeter. So this might look like 70/20 divided by the quantity of 60 times 2.54 cubed, 2.54 caret 3. So I get 7.14. So it matches up with zinc. So just a density problem on number 6, something back from chapter 1. 7, rhenium has 2 natural occurring isotopes. The 2 isotopes are noted. What is the percent abundance of the lighter isotope? This one might catch you off guard if you're looking at this before, say, Wednesday's lecture. The main idea here for any of the elements in the periodic table, we can get the average atomic weight from the periodic table. So we can look that up. Rhenium's atomic weight is 186.207 AMU. So the average atomic weight should be the fraction of the 1 times its abundance. So let's go fraction 1 times, let's call it 1 times 184.9530 AMU. And then plus fraction 2, which is 186.9560 AMU, that these sum up to 186.207. Okay, so see how the average atomic weight is closer to the 186, further from the 184? We want the abundance of the lighter. Do you see how the lesser abundant isotope is going to be less abundant, since the mass is closer to that of the heavier isotope? So the average atomic weight is closer to the heavier isotope, so the heavier isotope is going to be more abundant than the lighter isotope. Now, one other fact that we would know, since this element only has 2 natural occurring isotopes, whatever the fraction of 1 is, add to the fraction of 2 has to add together to unity. So it's either 1 or it's the other. So if you imagine it's 0.25 or 25% of this, then it's going to be 0.75 or 75% of the other. So those two go kind of hand in hand. Now we can do a plug and chug style problem where, we maybe want to solve for F1, then we know F2 would be 1 minus F1. So we could sub that in and say, okay, well, let's sub this in as 1 minus F1, right? Because F2 would be equal to 1 minus F1. And we could algebraically work that out and solve for F1, and that's what we're looking for in the problem, the fraction of that lighter isotope. Now, we could also recognize it's probably going to be one of those 3 and just do a simple plug and chug. So, whichever way we prefer doesn't quite make too much of a difference. It's just a little bit more algebraically challenging to solve it mathematically. Well, what the heck? Let's solve it mathematically here. I need a little more space to do this. So if we're going to work this out mathematically, I might set this up as, let me use some of the space down here, or over on the side perhaps. So let's set this up as we would have F1 times 184.9530 plus 186.9560 minus F1 times 186.9560, that all of that is going to be equal to the average atomic weight, 186.207. And so I can subtract this over to the other side. So let me do that. Find a better calculator. So we're just going to do 186.207 minus 186.9560. It gives me negative. So once I do the subtraction, this is gone. We do the subtraction and it equals minus 0.749. So if I were to rewrite that, that would be equal to this minus this. So F1 times that number minus F1 times that number. And so if I had, 4x minus 5x, that would be equal to what, minus 1x. So that's what we're going to do here. So we're going to take 184.9530 minus 186.9560. Do that subtraction. So I get minus 2.003 0 times F1 is equal to minus 0.749. So solve for F1. So take minus 0.749, divide by the answer. Here I get 37, well, a fraction, 0.3739. And so that's looking like 37.40%. So this is the fraction, that's the lighter one. So the percentage would just be this times 100%. So 37.4% is the lighter isotope, the remaining is the heavier isotope. Now, like I said, just go plug and chug if you have to. If you want to solve this a little more quickly, you can use a variety of problem-solving skills on multiple choice exams. Sig fig problem below for number 8. We've seen these hopefully enough times that this is going to be 3 sig figs because we keep the tens place, it's going to be 10.0. Out to the tens place, we note it has 3 sig figs. Divide that by 1 times 9. So we're going to divide that by 9.00 seconds. The 4 total digits, so 3 zeros. So the final result should have 3 significant figures. All right, that's solutions for this quiz. Thanks for the attention.